Hello, boys and girls. Today, I'd like to introduce you a very exciting, beautiful world of mathematics. It's called geometry. Before everything starts, let's think about a very simple question. I think a lot of people knows the sum of the triangle's interior angles is A, B, C, and angle A and angle B, angle C. The sum of them is 180 degrees. But I'm not sure if you ever think about why is this? Why the interior angle of the triangle is 180 degrees? Okay, I think some of the students might already know that. The proof is something like this. We draw a parallel line called DE. DE is parallel to BC. And then we got angle 1, angle 2 here. And then angle 1 equals to angle B, angle 2 equals angle C. This is because they are internal alternate angles. And then angle A plus angle 1 plus angle 2 is actually a line equals angle DAE. Because DAE is a line, so it's 180 degrees. Okay, pretty simple, clear. But I want to challenge you a little bit more on that. So did you ever think about why the internal alternative angle are equal? Which means why angle 1 is equal to angle B? Did you ever think about that? Or let's push a little bit further. Why this line, the angle DAE, is 180 degree? Why? You think, oh, this is a straight line, but why is that? Did you ever think about that? Or let's go even further. Why can we draw these parallel lines at all? In which would say, hey, there are a straight line BC, and through the point A, you definitely can draw as parallel. Whoever tell you on that? I think this is the interesting piece. Is I want through this course you do not just learn about how to get mathematical thinking, how to solve these geometry problems, but mathematical thinking is very important. Challenge everything that it's not obvious to you. I think this is the most important piece. Okay, in order to answer those questions, we need to go back a little bit to see some famous mathematician. I think this guy. He is called Euclid. You see, he is using a campus and drawing some geometry and teach his students on the mathematics and the geometries. So who is Euclid? Euclid is a Greek mathematician. He lives 300 BC, 2,300 years ago, it's a long time ago. But the most important piece is we think Euclid is the father of geometry. Actually, before Euclid, a lot of mathematicians works on geometry and teaches geometry and research geometry. But we call Euclid the father of the geometry because of this book. This is called the Elements. The Elements. This is the very famous book. So actually, this is the second most popular book in the Western society. The first one, of course, it's the Bible. But think about this one. It's a math textbook. It becomes the second most popular book. So that shows you how important it is. Of course, the first version is written in Greek, so this one we look in English version is actually translated in the later times. So this book is so important for the mathematical world. It works like sometimes as a Bible. For example, I think a lot of people knows this one in a right angle as A, B, C. So we have the relationship like A square equals plus B square equals C squares. Okay, so a lot of times we put this as I dot 47. What does that mean, I dot 47? This is actually the first volume of this element. First volume. And this is the proposition 47. Which means if you open this book and find the 47, the first volume of this book, you'll find the 47th proposition, you will find this formula. So, you know, the number becomes some reference book. You can think about like in a Bible, you can reference which chapter, which line. Let's start reading on that. The elements is something like that. There are some terms in the Euclid's Elements book. So we have definitions. We have 23 definitions. We have postulates. There are 5 postulates, and we have 5 common notions as well. And through these definitions, postulates, and the common notions, we can have a lot of propositions. And propositions, once you prove the propositions, you can use it to prove further propositions. Don't worry about these terms. We will introduce them one by one in the next slides. Okay, let's talk about what is the definition. There are a bunch of definitions, but we just talk some of them. You will see like definition 1 is like a point that you have no part. The point is a part, no part. It's very straightforward. A line is a breadth length. So a line, there's no width. This is a line. If it's a width, it becomes a plane, a square. The end of a line are points. Yeah, this end of a line is a point. And a straight line is a line which lies evenly with the point itself. So this basically means a line you can have see a lot of small points that comes with this line. There are a bunch of them. Then I pick some important ones. This says when there's a line, straight line, and there's another line standing on this straight line that make the adjacent angles equal to each other. So this one, angle 1 and angle 2 equals to each other. Then we define, this is the definition, define the equal angles is right. We call the right angles. Right angles is coming here, it's defined. You see, in this book, we now know the right angle is 90 degrees, but in this book, we never use the 19 degrees. Why? Because the right angle is the important piece. It's the entity itself. 90 degrees is just a representation of this like right angle. You know, this is called a degree system. In the future, you will learn other system like half of the pi. You can represent a right degree there. It's in another system. But in the whole book, we don't use this number. We don't use this number. We don't use pi. We just say this is the right angle. And this is called a perpendicular. Okay, I think it's straightforward. So a lot of stuff you think is taken for granted, but in this book, it just a defined definition. It defined clearly. This is the thing we need to assume. This is the definition of a circle. What is a circle? It's a plane figure. So this is a 2D circle. A lot of stuff only work on 2D. So if it's a 3D, then it's a different topic. So the plane is a line that all the straight line falling upon it from one point among those line with the figure equals to one another. So basically, there's a line, and there's all the straight lines falling upon it from one point, from some point. They are equal when each other. And then if you know that what is that point, that point is called the center of a circle. So this is a center. So this is a definition of a circle, and you know it's simple, and I think everybody knows that. But this is the formal definition in this Euclid Elements book. And there are others about triangles. I just omit there. And this is a parallel lines. This is also interesting. So parallel lines are first of all, it's on the same plane, and then it could be produced indefinitely on both directions, but they do not meet each other. So basically, this is the definition for parallel lines. They have two lines, and then you can extend it, use a different color. You can extend it indefinitely, and they do not meet each other. Then we call the parallel lines. This is another simple, interesting example. Is if you see a cube, you see this line here and this line here. Okay, you can extend it, but because they are not in the same plane, they will not meet each other as well. But do we call it a parallel straight lines? No, we don't call it. We need it in the same plane. That is, a lot of this geometry need in the same plane. We call it. In the 3D world, it's a totally different beast. Okay, then we go to the postulate. Postulate is something that we assume. But you will think it's why we assume that it's straightforward. It's there, but these actually give you a lot of hidden assumptions there. So postulate one: to draw a straight line from any point to any point, which means you have a one point, you have another point, you can draw a straight line. You see, of course we can, but this actually gives you a very important assumption, meaning this space, this plane is continuous. Think about, you have two tables. One table. There's another table next to you. There's one point here, and then another point in another table, but they are not connected to each other. You will not able to draw a straight line to this point because the table are not connected. So in this very simple, straightforward line, it actually has a very strong assumption that it's continuous. The space is continuous. It's nothing you can stop like this one. Okay, let me erase this and talk about the second one. So to produce a finite straight line continuously in a straight line, what does that mean? That means is if you have a straight line, then you can always extend it. You can always extend it. You can always extend it. What it essentially means is its assumption is there is unlimited space. This is a kind of a continuous. So to describe a circle with any center and radius, this is also so a lot of people think, why we have this? Well, our previous definition 10, we already talk about, what is a circle? There's a center and there's a line that each line to this center is the same distance, right? But why we need this one? So this is assertion. Assertion means we assume it exists. That is the definition. The difference between the assertion and the definition is definition doesn't make sure it exists. For example, we can define what is a ghost, but it didn't exist. In the real world, there are no ghosts. It's the same as a unicorn. We can think about a unicorn, we can define unicorn, but in the world there are no unicorn. So this postulate that is say, hey, in the world there's a unicorn, there's a circle. We can draw a circle there. This is another interesting piece, is that all the right angles equal to each other. You think, oh, all the right angles are 90 degrees. 90 degrees, of course, they are equals to each other. But going back to Euclid's world, they don't have these degree systems. They just have, for the whole book, there are no degree systems, no 90 degrees. But it's using a right angles as a unit. So what is like a straight line? We call it 180 degrees. In the Euclid book, we call it two right angles. Okay, so this means right angle there and equal to each other, and the most important is it make it the properties that it can work as a unit of the angles. Okay, this is the most, how to say it, a lot of discussion argument on this postulate. The postulate is, it's a very long sentence. I'll talk about it one by one. So that is, if the straight line fall into two straight lines, that a straight line fall into two straight lines, that the interior angle on the same side, this is the interior angle, and we need to find the same side, and less than two right angles. You see, that's the previous postulate. Right angle becomes a unit. Less than two right angles. This one is less than two right angles. Then the two straight lines, if produced indefinitely, let's choose a different. If it produced indefinitely, they will meet on the side of which. So it says they will definitely meet. Then we previously have the a parallel definition that two lines will never meet in the same plane whenever you produce indefinitely, and that's called a parallel lines. Then this is defined, say, okay, if there are two lines and they are not right angles, two right angles, then it will definitely meet. And the angles that are less than two right angles, these one are less than two right angles. So if you have a very very big one, so it shows you this one will definitely less than two right angles. Okay. This is the postulate 5. A lot of people, I think you will have this question as well. Actually, a lot of people think, first of all, this one is different than the previous 4 postulate. Previous 4 is just one line, and it's like very simple and very straightforward. But this one has a lot of wording there. I think it's why this looks not beautiful. And a lot of mathematicians want to say, hey, how about if we don't use this and we're just using others, so we can prove this system will work. Actually, all of them failed. This is a very important postulate for the Euclidean geometry. We call it Euclidean geometry. Some mathematicians say yes, other definitions and other postulates are fine. If we don't have the postulate 5, it will work as well, but it will create another system. It's not a Euclidean geometry, it's a different system for geometry. And that different geometry still works, but it's a lot of weird properties there. So that's why in order to make this like a 2D Euclidean geometry work, we need this postulate. And you can check online to see this postulate 5. You will see a lot of interesting articles there. And now we just simple explain to you what it is. And it's actually assume the parallel. It's actually assert the parallel lines exist. Remember that definition 23, which is define what is the parallel lines, and these postulate 5 assert it exists, just like we previously asserted the circle exists. Okay, the last piece is some common notions. That's some easy things, but it's not so. Things are equal to the same thing are equal to 1. That is, AB if AB equals AC, and AC equals DE, okay, then AB equals DE, okay, this is nothing there. If equals be added to equals, the whole are equal. What does that mean? Says if A equals B, then if added some same C, the whole will be equal as well. Straightforward. So if the equal subtract, the remainder is the same thing. Like say, if A equals B, then A minus C equals B minus C. Okay. Things which coincide with one other are equal to one another. This is say, if you have a coincide, actually means like a perfectly overlap. Think about it, you have a triangle. If you can pull this triangle up, cut this triangle, and then move to another place, and if this one can fully overlap, exactly overlap, and another one, they are coincide. And once they are coincide, means they are exactly equal to each other. Each edge are same, each angle are same. Then the whole is greater than the part. This is, say, how to say this? You have a whole pie, then this is a part of the pie, and the whole, of course, is greater than the part. And this is also true to the angle, so you can put this angle. So if you have a part of the angle, then the whole angle will be greater than the part of the angle. Okay, so the common notions looks like very straightforward and simple, but Euclid defined it clearly, then that's all we need. So you will see 23 definitions,
5 postulates and 5 combinations. That's all you need. And from now on, if you see some theory of this, in this geometry world, then you will challenge them. Why this happens? Because it's not in that definition, not in the postulate, not in the common notions. It must be proved. Only those stuff does not need to be proved or cannot be proved because we assume that is correct. Everything else should be proved to be true to use. Then during this whole book, we are able to learn how to prove that. Okay, we talk about definitions, postulates, and the common notions and the propositions. So let's get to work. So I want to show some examples to show how we use those information to prove the theory. Here, the first example is I.13, which means the first volume of the Euclid's Elements book, and this is the proposition 13. The proposition 13 says if a straight line stood on another straight line, say we have a straight line CD, and another straight line is EB or AB, it will certainly either make 2 right angles or the sum of the two angles is equal to 2 right angles. What does that mean? So that means if we have a line and we have another straight line, it could be only 2 cases. One is EB, which is perpendicular to CD, that it will make 2 right angles. Or if it's AB, it's not perpendicular to CD. The sum of ABC and ABD will be 2 right angles. How to prove that? This is simple. One, if it's perpendicular, like EB is perpendicular to DC, then we got 2 right angles. This is the definition 10, D10. We go reference to by definition and then done. And second, if it's not perpendicular like AB, so we will have like angle EBA. Here, this one EBA plus angle ABC plus angle EBD equals 180 degrees, or 2 right angles. Why? Because from the point B, we can always draw a straight line that is perpendicular to CD. This is actually the proposition I.11. So you can find, I just skipped there. And then once you have that one, it becomes straightforward because EBC is a right angle, and EBC could make up as ABC plus EBA. Then you get this. Okay. The second example is I.15. So let 2 straight lines AB and CD cut one another at a point E. Then I say the angle AEC is equal to DEB, or the angle CEB is equal to angle AED. Okay, so how to prove that? We leverage previous propositions. Let's see, angle AEC plus angle
CEB is equal to 2 right angles. Okay, because they are straight line, AEB is straight line. This is exactly the proposition 13 we proved before. Okay. The second step is on the other line, it's the same. That is choose a different color. Angle DEB plus angle CEB equals 2 right angles. Again, it's the same as proposition 13. Okay, so CEB and CEB are same, and on the other equation, they are all total right angles are same. So what we can conclude? Conclude AEC is equal to DEB. Then we can prove on the other angle it's the same. Okay, then this is going to our alternative internal angles. So a straight line falling across a parallel straight lines make the alternative angles equal to one another. Alternative means this one is equal to this one. BGH is equal to GHC. Or on the same side, we just proved this one as a simple. So why this happens? Well, this is the same as before, because when we go back to the postulate 5, it says if it's two parallel lines, then angle AGH plus angle CHG equals 2 right angles. The postulate 5 is not saying exactly same thing, but it says actually the reverse way. Say if the AGH plus CHG is less than 2 right angles, then AB and CD will meet when you extend the line. So this it says it's a parallel lines, which means they will never meet. Then we can conclude AGH plus CHG equals 2 right angles. Okay, with this one, everything becomes much easier. From I dot 11, we will know. Oh, it's 13. Sorry. From I dot 13, we know angle AGE plus angle AGH equals 2 right angles. Okay, and then you will see AGH, they are same, and 2 right angles are same. So we conclude AGE is equal to CHG. This one. This is angle 1, angle 2. And because of the proposition 15, we know that AGE is equal to BGH. Then we get the final result here. Angle BGH equals to angle GHC. This is our problem proof.
Okay, now we go back to the first question. Why the sum of a triangle interior is 180 degrees? Again, we do this one, it's the same, A, B, C, D, E. But now we can have this one. Why the alternative internal angles are equal? This is because the proposition 29 we just proved on previous slides. When the angle of a straight line is 180 degrees, this is the same. This is the definition 10 of the elements book. Why we can draw a parallel line at all? This is actually we call the Playfair axiom. Playfair is another mathematician's name, but basically this is a postulation 5, a variant of postulate 5. And if you are interested, you can see how to prove that. It's fairly straightforward, but it needs another proposition 27's help to do that. Basically, it says if there's a line, you can point, then you can draw a straight line that is perpendicular to this point, and then you can again draw another line to perpendicular to this line. We say A, B, C, D, E, F. So basically, you have an AB, and you can draw a straight line CF that's perpendicular to AB, and then you can draw another straight line DE that's perpendicular to CF. Because they are all perpendicular, so they add up to 2 right angles, then they are parallel. But this is not the exact proof, so if you are interested, you can try and take how to prove that. Wow, it's a long journey here. Hope you enjoy this session. So we will have a lot of more on the geometry and the Euclid's elements. This is just the beginning. If you have any questions, feel free to let me know, and I can answer you if possible. Thank you. Bye.